Hi, I'm Yasha Pushak. Thanks for joining today. Automated machine learning has recently made great improvements in terms of making machine learning easier to use. But how does it work when you don't actually have any labels for your dataset, which means that it doesn't know when a model is doing a good job? I'm a senior member of technical staff on the Oracle Labs AutoMLx team, and today we're going to talk about unsupervised anomaly detection, which is exactly this. It's where you're given a dataset that has no labels, and the goal is just to identify the unusual data points in your dataset. Depending on your application, this could correspond to, for example, a security threat or a disease. In these cases, usually users are required to provide what's called the contamination factor. This is just the percentage of data points in your dataset that look strange, that are anomalies. In practice, we find that most of our users don't actually know this contamination factor. Nevertheless, anomaly detection algorithms take each data point in your dataset. They try to learn which points look normal so that they can rank each point on an anomaly score. The higher the anomaly score, the more weird the point looks. The lower the anomaly score, the more normal. If you combine this with the contamination factor, you can then actually get a prediction about whether or not each point in your dataset is an anomaly. There are a bunch of different methods out there, different anomaly detection algorithms. And as it turns out, no one algorithm actually works best on all datasets. So we support a broad range of different techniques to allow you to get the best possible performance for your dataset. We take in your dataset and we make all of this very easy to use. We automatically pre-process your dataset, we pick the best anomaly detection algorithm for you, and then we optimize its hyperparameters to give you a high quality performance. Finally, once you've got this machine learning model, we then offer insights into what it has learned so that you can know whether or not you want to trust it or whether or not it's made the right decisions for each point. We seek to make all of this very easy for you to use. We've designed a simple interface. You simply import our package, initialize our model, pass it the dataset. Again, no labels required, and then you're good to go. You can make predictions. Let's take a look at what this looks like with a simple example. In this dataset, you can see that the normal points are blue and the anomalies are orange. Using a simple model, principal components analysis, with two different contamination factors, you can see the result there on the right. On the top, you've got a small contamination factor. That black circle is the decision boundary. So all of the points outside of that circle are what the model believes are anomalies, and anything inside is what it believes are normal. And at the bottom, you've got a larger contamination factor. You can see in both cases, the model isn't always getting all of the right answers. In some cases, it has too many anomalies, and others too few. With Oracle AutoML, we seek to do all of this for you. So this green line now represents the decision boundary from our model. So you can see in this case that almost all of the anomalies are outside of the green line. And remember, we're automatically learning what the contamination factor is for you. It's not something that you have to provide. Let's take a look at a few more examples on more data sets. Here we've actually got three different anomaly detection algorithms: principal components analysis, k-nearest neighbors, and one-class support vector machines. Again, we've got three different data sets with two different contamination factors. And you can see that sometimes they do a bit better, but overall, most of these models are making mistakes. On the other hand, on the right, you can see what was provided with our method. Here you can see that we're automatically learning the contamination factor and providing reasonable predictions for the different data sets. All right, so how do we actually do this, right? How do we actually identify what model is doing a good job when we don't have any labels at all? We've got two different methods for this. The first one is Unify 95. The idea here is all about separating the anomaly scores for the anomalous points from the normal points. So intuitively, if a model is doing a good job, then you would expect it to be able to provide high anomaly values, high scores for the points that are actually anomalous, and low scores for the points that are actually normal. Now, anomaly scores, they're not normalized. They come on different ranges for different models and different data sets. So first we apply a state-of-the-art normalization technique to get them all into the range 0 and 1. Then we use a simple heuristic. Any point that's above the value 0.95, we label as anomalies. Any value that's below that, we label it as normal. It's a simple rule, but we found that it works fairly well on a large number of datasets. Next, we say that a model is doing well if the points that are labeled as anomaly are farther away from the points that are labeled as normal. Our next method is called N-1 experts, and it's all about leveraging complementary information from the different models. Our hypothesis here is that each anomaly detection algorithm essentially represents some expert's belief about what an anomaly looks like in your dataset. So if multiple different models agree on what the anomalies are in your dataset, then quite likely they're right. So what we do is simple. We let each model take turns being a candidate and an expert. So in fact, each model is going to score one of the other models. And then we pick the model that has the best average score according to all of these experts. We're essentially trying to pick the most consensus model. Now there's one very recent method out there called MetaOD. To the best of our knowledge, this is the only existing unsupervised anomaly detection method other than our own. Now this method actually requires a set of historical datasets with labels. And then it tries to learn, based on these datasets, a way of identifying which new dataset is most represented by your old one. So it's trying to find an old dataset that looks similar to your new dataset. Because it has the labels on these old historical datasets, it can then look up which machine learning method works best on that old dataset and recommends it to you for your new one. This works pretty well if you have a set of historical datasets that are relatively similar to your new datasets and that have labels. Of the three methods, we observed that N-1 experts and MetaOD tended to perform the best. We recently published on this at the 2022 AutoML conference. So let's take a look at this figure on the right here. On the y-axis, we've got the MetaOD scores, and on the x-axis, we've got the N-1 expert scores. So in both cases, smaller is better. Each point in this graph represents a different dataset. So all of the points that are above that diagonal line mean that N-1 experts is picking a better model. And you can see that on almost all of the datasets, we're actually finding better models. All right, so once you've got this model, you need to be able to understand it. And that's where explainability comes in. Again, we've designed a simple to use interface. You simply pass us your model and your dataset, and then you can get the explanations directly. But why does this matter? Well, as machine learning models become more complex, their performance gets better, but our ability to understand them gets worse. And this means that we're less likely to adopt them in critical decision-making domains, especially where humans are involved. In fact, in a lot of cases, humans now have a right to an explanation, and you need to be able to tell them why you made your decisions. You could use simpler models, but of course you pay the penalty then with worse accuracy. This is where machine learning explainability comes in. It helps improve your understanding and increases trust in the models. We do this not just for simple models, but for any model. Now, in particular, in this talk, I'm going to focus on local explanations, which is where we're trying to explain why a model made a particular prediction, although we do have other variants as well. Let's take a look at an example. In this dataset, we're trying to detect whether or not patients have cardiac arrhythmia, irregular heart rhythms. So on the left there, you're seeing an example of the feature importance. In fact, what this is saying is that all of the features contributed a little bit or a lot to increasing the model's prediction of the point being an anomaly. So the most important feature is the one at the top there, the QT interval, which has a value of 237. Now, if you're like me, you're not a medical expert, so you don't know what that means. Nevertheless, if you give this information to a medical expert, they can then decide whether or not this point actually is an anomaly. And you can see an example of this on the right here, where we're showing the scatter plot with the top two most important features, the QT interval and the weight. And even from this graph alone, you can see that yes, this particular data point does look weird with respect to the rest of the data. Now I did a quick Google search because I was curious, and it turns out that there's actually something called short QT syndrome. It's a rare genetic disorder that causes you to have an irregular heart rhythm. And what it means is actually that the beginning of your heartbeat in the first chamber of your heart is followed too quickly by the end of the heartbeat in the second chamber of your heart. And based on this value, the patient would actually be classified as having this syndrome. So how do we give you this kind of information? Well, we have a general recipe that we follow. First, we take one or more of the features in your dataset and we actually just modify the values of the feature. This then essentially unlinks the values of these features from the original predictions. So we get your model then to repredict with these new modified copies of your row in your dataset. And then we analyze the difference between the original prediction and these new modified predictions. We repeat and average this over different features, which allows us to tell which of the features were the most important and whether or not they increased or decreased the model's prediction probability. Now, I've so far just spoken about anomaly detection, which is just one of the tasks that we support. We also support the more common ones like classification and regression, as well as forecasting. We have a large number of different machine learning algorithms, including all of the popular ones like LightGBM, XGBoost, and simple feed-forward neural networks. We support different data types, tabular, text, and time series, and we have actually quite a number of different explanation methods, which can be used for different tasks and purposes. If you'd like to learn more about automated machine learning and explainability, you can check out some of our other sessions at Oracle CloudWorld 2022. For example, in the first session there, we talk about our supervised pipeline. We also have some sessions specifically dedicated to examples, for example, to learn about how healthy our oysters are, or how you can use AutoML to improve healthcare. The last one there talks about using machine learning to predict the location of watercraft vessels. Thanks for joining.